So we're getting about time here, so let's settle in and get started. I'm Lawrence Crowl. I am going to wander through the implementation of value types today. If you are not here in the room and are not listening to this talk, then you might want to read the notes. The first thing we need to settle on is what is a value type? Okay, there are two main things that I think are important to get from value types. One is that the identity is not important, right? Its address is meaningless. In fact, it can have meaning without an address, which makes operating on a copy of the object indistinguishable from operating on the original object. The second thing we want to worry about is that the operation is independent of the context. So changes to the context or operations on the type don't interfere with each other. These have a lot of implications, and you'll find different definitions for value types, but this is good enough to get us going. What are the most familiar value types we use? Well, the built-in arithmetic types are the prototype value types. Those are the things people think of. The other thing we have is strings. We often use strings as value types. We create them, we pass them around, etc. But they're not really quite value types. It's complicated. I'll get into that a little bit later. Value types, the built-in value types of arithmetic have a lot of valuable attributes. I won't go through them all. You can read them later. In fact, those attributes are so valuable that programmers will use them even for things they weren't really intended for. You can compare apples and oranges because you're using a value type, right? Green cannot be green because you're using a value type. So why is it that people are using all these built-in value types and not building their own abstractions to represent core values in their system? If they were to use those abstractions, they would have a handle and a way to validate the consistency, ensure that operations are done properly, but they're not doing that. Why are they not doing that? Well, they're worried. They're not just worried, they're afraid. Okay? What are they afraid of? What are their concerns? Well, the list is fairly long, but it basically boils down to it will not be good as a built-in value type. They're afraid they're going to lose something. Performance, correctness, portability, whatever. They're afraid of that. So if you're going to implement a value type, you need to overcome their fear. You need to make a type that's efficient and bulletproof. The first step in this is understanding what operations you want on the type. What makes sense, what does not. However, in a value type, there is mission creep. Every operation you add could potentially require a change in the operation or much higher cost in the operations. With subtraction, we suddenly had to figure out how to represent signed numbers. There were 3 different representations of signed numbers popular in early computing days. When we added division to integers, we took a fork in the path. Commercial operations tended to use quotient and remainder. Scientific applications invented floating point. Mathematical applications often went to rational numbers. So now, because we added one little operation, we're suddenly in 3 different worlds. And you need to decide which world you're going to be in when you add an operation. So the way to worry about operations is ask yourself, which category of operation is this? Is this something I must have? Is this something I'd like to have? Okay, exuberant generalization. The C++ committee has been guilty of that one. Foolish consistency. Well, the C++ committee has also been guilty of that. You need to figure out what is really important. So focus on the must-have operations. Implement those. Once you have those working, then you can go through the nice-to-haves and implement those that you can do so without interfering with the representation or the other operations, and then ignore the rest. Because if you implement the rest, you're now suddenly committed. You'll have customers and you can't change it. Whereas if you don't implement those, then you have more flexibility for change in the future. There are some properties of every type and operation we implement. And these things are often not obvious in the code. So what we want to do is think about them ahead of time so that we don't surprise ourselves or our customers. The first set is the mathematical operations, the mathematical properties. Go through all of these properties, see which ones matter to your types, which ones don't. The one I particularly want to point out to you is the strictly weakly ordered type. This is a requirement of most of the standard library. When you pass a type in that's going to be sorted, it has to be strictly weakly ordered. This is not obvious while reading the standard, and the implications of it are significant, and it's sometimes hard to tell whether or not a type is strictly weakly ordered. So this is the one I particularly want you to focus on when you're putting together your own type. There are representational properties. Types produce the least surprise when every bit pattern in the type has a distinct value. But that's not always possible or even desirable. But you don't want to let that go by accident. The next set of properties is semantic. Are errors in the use of your type detectable at runtime during debugging? Have you let container attributes sneak into your value type? All of those things need to be addressed. In particular, with std string, it was designed as a container. People are trying to use it as a value, and that dichotomy has caused significant trouble to the C++ Standards Committee. Yes?
Can you give an example of that, out of curiosity?
Well, in particular for C++ 11, we introduced concurrency. And it turns out that the definition we had prior to that made it difficult for a programmer to determine whether or not something could be used safely concurrently. And the result is at least one vendor had to change the way they implemented std string and therefore invalidated all previous binaries that used std string. That's a pretty big problem. The next thing you want to look at is what are the syntactic properties you are imposing on your user. Look at how users write their code and see, does this make sense? Is the way they write their code going to be efficient in the way that I've implemented the code? And I'll give you an example of where that didn't quite work out. String append. The append operator plus equals, stack them up, and everything works right. No, because actually plus equal is right associative, which means you're modifying A, B, and C in the process of this. To fix it, you have to put in parentheses. Who likes doing that? I don't. In contrast, if you look at the left shift operator used by the stream class, it's left associative, everything works out, it's efficient, it's convenient, it's easy, it's the right way to go. But of course, we're already committed to plus equals. The next thing you want to think about when you're writing a value type is the generality. Arithmetic types can be used in several places in the standard where normal class types can't be. We would like to use our new value class in those places. And the mechanism for this is called literal types. What it does is it allows you to create compile time constants. It allows you to use those types in the computation of array sizes. And probably most importantly, it allows you to use them as non-type template arguments. So suddenly, you can use a value type color that has all the same usability as the integer 3 in instantiating a template. There are several requirements on how you build up a literal type. The general message I want you to get is these requirements require a little care, but they're actually not all that onerous for small types. When you start getting the bigger types, then it becomes more difficult to happen and probably won't. But for the smaller types, you can make it happen. The next thing you want to think about is, do you want literal values? We can write 3 in the source code, and it will turn into a value and carry on. We have a feature called user-defined literals, or literal operators, that enables you to support literal values for your type. It can be a bit challenging to write a user-defined literal, a literal operator, that is also const expr. Right? You'd really write your literals to be constants also. That takes a bit of work. The other thing you have to worry about is everybody wants a short literal suffix. So everybody wants _p, _s. And you're not allowed to have just s because the standard has taken that. In fact, the standard has taken every literal that doesn't start with an underscore. But the result is there's now a land rush for short user-defined literals, so you need to be very careful about what you're doing. You can use some scoping and nested namespace issues to try and control that. I would use Google to get some examples. One more thing before I do that. Some people have used user-defined literals to do things like kilometers. The mechanism is actually a poor match for doing units. So I recommend you stay away from that. The next topic is the representation. The representation you choose can have a large influence on the usability and performance of the type. It probably will not surprise you if I tell you that you should remove redundancy from your literal types, because redundancy is bad, right? Well, not always. For instance, if you have a complex number and you look at the implementation of various complex operations, sometimes it's better to have them in a Cartesian representation and sometimes in a polar representation. You can have a type, if it's mostly read and only occasionally changed, you can keep both representations. So an operation like multiplication that might be a little better with polar coordinates just pulls those out. The magnitude. It's already in a polar representation. You don't need to do anything. You just pull it out. And a Cartesian representation, well, that's a few multiplications and a square root. So the redundancy can help. Yes?
But how is that going to help you if you create a new read mostly complex and you have to still compute real and imaginary from that? So even if it's easier to use that in angle and polar coordinates, if you still have to compute the Cartesian coordinates as well.
Like I said, it has to be read mostly. So you're going to create a value, stick it in, say, a global table, and it gets read most of the time. It might get read 1,000 times before somebody gets around to changing it. Okay? So it very much depends on your application area, right? The value types are often tuned to the application area. Padding. You want to try and avoid having any padding in your type for a number of reasons. The biggest one is smaller is faster. You don't always know what platform you're going to be running on. So you want to try and set up the fields in your type so that they're pretty much padding free wherever it goes. So if you allocate from the top down in the left-hand column, for most platforms, you won't end up with any padding. The column on the right, things are a bit iffy. You'll have to worry about that specially. If you're getting desperate, you can test with the preprocessor and adjust there.
I have a question.
Sure.
When you say don't get any padding, you mean don't get any unnecessary extra padding? Because obviously if you have an int in the char, you're going to get padding.
Right. You want to avoid any unnecessary padding. There are a couple of rare cases where any padding at all can affect your code. But for the most part, you don't have to worry about that. The next thing you want to worry about is how hot are the various fields in your class. So for a small class, it's all going to fit on one cache line. There's nothing to think about. You're done. As types get larger, sometimes you have situations where one field is not often accessed. It's a backup field. You want to move that off of the main cache line so it never gets loaded, and you avoid that memory traffic. If you have two fields that are accessed together, you want to make sure they're on the same cache line.
This is very architecture dependent. If you're writing code that can run multiple different CPU architectures, you may not be able to do this.
Yes, it depends on what architecture you're on. But by and large, if you move the hot stuff to the front and the cold stuff to the back, you'll get the best you can for whatever architecture you're on. Copying and moving data is a major cost on modern systems. Let's see if we can get that down, get that cost down. The best thing you can do for copy performance is to make it trivial. The machine is fastest when copying an undifferentiated set of bits. The minute you require imposing semantics on pieces of that bits, things are going to get slower. It also has another advantage is if you have a trivially copyable class, sometimes it can be passed in registers, which will improve performance. And in fact, it's testable. There's mechanisms in the language that allow you to find out. The requirements for trivially copyable are a bit detailed, but they're generally not onerous for the small, simple value types. But what if the type is big? Well, live with it. Because if you try to get fancy in keeping the size small in one place and putting extra stuff elsewhere, you're now hitting at least two different cache lines. And you might end up being slower than just copying more data. But not always. So what if your type is too big? Well, what you want to do is make sure that you implement logical copying, even if you're not physically copying, which means copy on write. Now, if you've got copy on write, you need to know when to delete the shared copy. Reference counting works well for non-circular data structures. But we're in a new world. Concurrency is here. You need to make sure that reference counting is thread safe, unless you happen to know it's not in a thread shared context. The other thing you want to look at is if you have a type that could be very big but could be very small, look at embedding small values in the struct itself, in the main type, with a bit saying whether or not it's embedded or whether you have to go to external storage. This is used with std string. It's called the small string optimization. Most modern implementations do that. Moving can be a big performance improvement for those types that are not just all in the main thing. And particularly if you have reference counted storage, you can avoid the cost of having that storage of that reference count or copying the data. Here is a case where we have a deep copy. If we move, so whenever we copy it, we have to allocate a new one, reinitialize it from that, so on. If we have a move, all we do is steal the pointer and null it in the last one and carry on. So this can be a huge performance improvement. Next topic is parameter passing. It too can have a significant effect on your performance and your semantics. You have two choices, pass by value and pass by const reference. Traditionally, nearly every class has been passed by const reference, but that choice is not always the best choice. But before I go into a detailed assessment of which way is best for performance, I want to talk about slicing. If you have const ref, you can get different function results than if you have a value copy. In particular, virtual functions no longer get looked up if you're doing a value, because you're extracting the base type from the original type. Whereas a const reference, you're keeping focused on the original type. This slicing, this difference in behavior when you have virtual functions or not, may or may not be what you want. It probably isn't what you want logically, but you have the opportunity to do some adaptive computation if you do the const ref through virtual functions. Okay, so you can have different implementations with different responses there. You might get better results, but we're doing value types. You probably want to make sure that the logical result is the same. So pass by value, the code is pretty simple. It does what you want. The only real problem here is that the implementation costs are defined by your vendor's ABI. And those costs can vary quite a bit for small items. The reason is there are basically two different ways to implement pass by value. The first one is by direct implementation, direct pass. This requires a trivially copyable class. On IA32, you push it to the stack. On AMD64, you can copy it to a register. On Spark32, you don't do either of those things. You punt to the next technique, which is to indirectly pass it. This involves allocating a temporary in the caller, initializing that temporary, copying into that temporary, passing a pointer to that temporary through the regular parameters. And then inside that function, you're now accessing that type indirectly, so there's an indirect memory cost. And then when you come back out of the function, you have to destroy that temporary copy. So it's potentially significantly slower. Pass by const ref, the second technique, has the indirect memory costs of the indirect pass. It doesn't have the implicit copying, but the problem is that when you do that, you could potentially end up with an alias. And in this example, if input and output are the same object, the code will overwrite itself. You'll get the wrong answer. I'm going to talk about aliasing a little bit later, but I wanted to give you some recommendations. This is the way I approach things. If your type is small, less than about 2 pointers, you want to make it, if it's trivially copyable, pass it in by value. Pass by const ref when the type is large, and by that I mean directly large, not indirectly large. And when alias detection is relatively cheap compared to the operations you're going to be putting on it. So there's a gap between those two. And if your type is in that gap, you want to think about doing some performance measurements. Yes, sorry.
Sorry, jumping back to slicing for a moment. I find that the discussion of that issue a little confusing because if a type has virtual methods, you normally can't keep it on the stack at all, which I think of as being sort of deeply related to being a value type. Do you see what I'm saying?
So you can keep a class with virtual methods on the stack, right?
Right. You can't do virtual calls.
But conceptually, polymorphism conceptually requires reference types, not value types. It's sort of
Right. This is why I was talking about logical versus physical, right? So you can implement something that's logically a value type, but inside the implementation, you use inheritance to take different execution paths. So if your data looks one way, you can use a separate implementation. The most important thing here is that if you do have virtuals, and the only way you can run into this problem is if you have virtuals. Then you want to think really hard about how you pass this and whether or not that virtual should be there. That's the basic takeaway. And you can come up with good reasons to pass virtual objects by value, but you need a good reason. You have to really think about it. For passing by Const Ref, that's the way most types are passed now. So you probably won't get fired if you do that, but you should think about it before you go on. Yes?
You were referring to aliasing passed by reference.
Right.
But what's the situation where I have to worry about aliasing if I'm passing by Const reference?
Well, here is exactly that situation. So in this code,
Yeah, but those aren't.
oh, sorry, that's a typo. It should say const type reference input. So what's happening here is the first line of the body is changing output, but that means it's also changed input. So in writing RF1, most people would not expect their input parameter to change. But because of that aliasing, it has now changed, and you end up tripping over yourself.
So in this particular case, one of those references is in const.
Well, the input one should have been had the const qualifier.
Okay.
That's a typo on my part.
Thank you.
So result passing. Well, we're talking about value types. Of course, you return by value. This is the best thing you can do for code clarity for a lot of things, not just value types. But the one thing I want to make sure you do is every function that returns a value, make sure it follows the named return value optimization. So you have a single variable, and every return statement just returns that variable. And if you want a different return value, assign to that variable. It's the best thing you can do for performance in C++.
How do you avoid slicing in that case?
There can't be any slicing because you're returning the same type. So in the call site, they're allocating a new storage space for that particular type. So now we're going to go into the discussion on aliasing. It's a major source of bugs, and it's a major inhibitor to performance with the compilers. You have basically three approaches. The first one is probably most commonly used. The second one is it's particularly used a lot by people that use the restrict keyword, which is not in C++, but nearly every compiler supports. The third thing you can do is overcome the problem. And I recommend that approach because you as a programmer of a value type are in the best position to prevent aliases. Okay? Sometimes it's not feasible, but I recommend that approach. The first technique for this is to copy a potentially aliasing parameter. You're in, just copy it and use the local temp. This is no better than writing a value parameter. So there's no reason to prefer this if you started from scratch. Sometimes, however, you are dealing with a legacy interface. Somebody else has already done a value type, and now you're in fixing it. So you may not have a choice, in which case this technique works when you can't change the interface. The next thing you can do is conditionally copy. Go in, test whether or not you have aliasing. If you have aliasing, then you create that temporary copy and carry on. This looks like a lot of code bloat, an additional comparison in the function. That's true. If the function is inlined, then the compiler can often determine that those two addresses can't be the same and get rid of all the junk, and you're back to the best case. The most common use of this conditional alias testing in code now is assignment operators, where you say, am I assigning to myself? Because this code, if I did not have that test, it would first delete and destroy P, and then I'd copy from a dangling pointer that's been trashed. So you'll often see this code in testing, in assignment operators, because it's necessary for correctness in the case that you're assigning to yourself. The next thing you can do is order reads before writes. So we can go ahead and do all our computation with our inputs, and then go ahead and do our modifications to the output. Now, the types, the temporary variables you create here, many of them will have already been created by the compiler. You're just giving them a name. Sometimes this may mean they last a little bit longer, but not to worry. Compilers are pretty good about eliminating trash. This is an implementation of the multiply assignment operator for complex numbers. It too is broken when assigning to yourself. So if you say A times equals A, this code is broken. We can address that problem by read caching the fields. So we'll read all the fields first, and then we'll do our computation and assign our results. Now, this is actually a good thing to do even when there's no aliasing. The reason is when the compiler looks at the original code, it sees that there's two pointers. It doesn't know whether or not they might be aliased. More importantly, it doesn't know whether or not you intended aliasing. And since aliasing is perfectly legal, it has to make tripping over itself valid code. Right? It has to assume that the aliasing is correct behavior, and this code is operating correctly in the presence of aliasing. Right? So we've got a situation where we wrote the obvious thing. It doesn't work with aliasing, but the compiler doesn't know that. So if we read cache our variables, we eliminate that confusion to the compiler, and it can start generating better code. Yes?
Is there a reason that you prefer this form over passing by value?
No. Well, it depends on how big it is, right? So if the class starts getting large, then I would, you might consider doing this.
So, and if you're not reading from the whole context, in other words?
Yeah. So for modern 64-bit architectures, classes of this size, you're better off passing by value because they have the small struct optimization in the calling convention. But this is a particular example because the complex number in the standard library is built this way because at the time it was designed, pretty much all structs were passed indirectly. And so they did it by Const Ref. Now all those library vendors probably had some bug they had to fix. But in any case, read caching your fields is a benefit to the compiler, whatever happens. Aliasing is not the only conflicts that you might run into. We have a number of conflicts with the environment that we need to take care of. There are a number of possibilities for conflicts within global state. I don't want to say you can't go to global state. What I want to say is the user should never have to see the effects of interacting with global state. That is, you don't want the users to think about global state at all. Okay? Memory allocation, that's fine. Physically shared state, like if you're doing copy on write, that's okay, but you got to make sure you protect it if you are not sharing all of the state read-only in all operations, then you probably need to be doing some locking. The next conflict is static initialization order. The C++ language has relatively few guarantees on what order global variables get initialized. For a value type, it would be best if you could initialize it at compile time or link time. Get that in there. It happens before the program starts. You don't have to worry about initialization order. The way you achieve that is with a const expr value constructor. If when you pass a constant to that constructor in the global initialization, it will get initialized at compile or link time. Okay? The downside to this technique is even if you want this to be, you're sure this should be static initialized. There's no way to write the code so that you'll get a warning or an error if it happens to not, if somebody happens to pass in a variable. Okay? So it's a kind of a hope programmers do the right thing approach, but you want to enable it.
When will the standards committee fix that?
That's a good question. Do you have a proposal?
We may talk.
Yes. There are a couple obvious ideas like attributes or something like that which we can look at. The next conflict you need to worry about is concurrency. The first step to avoiding concurrency interference is to reduce aliasing otherwise. We've already seen that aliasing is a bad thing. Go ahead, concentrate on getting rid of that aliasing. The next thing you want to do is make const reference parameters read safe. Okay? This is a requirement that the standard library places on all of the objects in the standard library. What it means is that if your type has a const ref parameter, you will not do any unprotected access to anything beyond that parameter itself and to that parameter. So, for instance, if I pass an operation to the library, it will not, if I pass, let me back up and say this. If I take a string from the standard library and it's referenced by const ref in the standard, you can be sure that the standard will not modify that object. Okay. That requirement is not made on user types, but I'm going to recommend that you follow that standard because it's a concurrent world. People are going to start expecting this. Get prepared for it now. Sir.
For concurrency, can you go back to that slide? I just want to point out that what you said there also implies is the committee discovered to its horror that mutable is deeply hostile to multi-threading. Mutable
Yes.
caches should be avoided if you follow this rule.
Yes, yes, exactly. Yeah, mutable and concurrency are not friends. The next conflict you can run into is exceptions. Exceptions are an unintended control flow. Programmers sometimes most of the time programmers would rather not have to worry about exceptions. And your goal in writing a value type is to make sure that they don't have to really worry about them. They might have to worry about them showing up. They don't want to have to clean up the litter from a badly handled exception. So you want to avoid throwing exceptions if you can. But if you can't, because they bubble up from the exception details, you want to make sure that all of your operations are exception safe. No except is your default. If you can't do that, you want to make sure that they're exception safe.
Strongly exception safe.
Yeah. So a couple of techniques. Allocate before you make any changes. Do all your resource acquisition, all of your allocation, before you make any changes to the type that's getting modified. Okay? And then, once you've done that, then you can do the switch and start deallocating resources. Because if you don't do this, then you'll delete before you have the actual data. But that code had a bug. And the bug was that if the delete of P fails, then we leaked resources. So if the delete of P fails, now we have to go back and delete Q. There are lots of tools in the standard that help you out. I suggest you use them, scoped pointers, things like that. But if you get down into the weeds, you want to make sure you follow along and take care of all of these details. The next topic is optimization. It's a partnership between you and the compiler. Most partnerships work best when you don't try to do the same thing. So concentrate on different tasks. And in particular, you are responsible for doing the things that the compiler cannot change. Right? The compiler cannot change the representation of your type. It's simply not allowed. It's part of the ABI. So you need to concentrate on that part of the task. Right? Many cases of an aliasing, the compiler can't remove it because it could be a potentially meaningful alias. So you want to concentrate on removing that. Pretty much everything else, leave it up to the compiler until it's proven guilty in a court of law. The second thing you want to do is avoid redundant memory accesses. If you load a pointer twice, that's going to be inefficient. It's going to get in the way of the compiler. And you shouldn't do it unless you are actively waiting for somebody else to change that pointer, the contents of what that pointer is pointing to. So if you're not waiting on somebody to change it, don't load it more than once. The keyword this is an implicit pointer. So all of your class member accesses have exactly that thing. It's really easy to write a class member function where you reload member variables several times. So you want to aggressively cache those fields like we talked about earlier. Some coding conventions have a trailing underscore for class member variables. That's actually quite handy because it becomes kind of obvious when you're reading from a field more than once. It's a good result. Once you do that read caching, now you'll get the compiler doing a better job on that class. Inlining. Inlining is probably the biggest decision you never want to make. The big problem is if you have any ABI binary compatibility constraints, writing an inline function could turn into a very long-term commitment. So you want to be careful about inlining. It basically says nothing about this type is ever going to change. Inlining, the performance can sometimes be erratic, right? Compilers may or may not inline it. This could give you inconsistent behavior in performance on various applications because compilers might hide the consequences. But you're going to have to make a choice. So my recommendation is inline if the code is going to be smaller than the call site. Otherwise, inline only when you have evidence that the performance matters. Yes?
Back here, talk about caching member variables. I'm sorry. The compiler is unable to optimize that?
So if you cache the member variables, okay, and the compiler inlines, most of that caching will probably end up going away anyway. And the reason is the compilers are very good at value propagation, right? Once it's in a local variable where it can see exactly how it gets touched and modified, the compiler can do an awfully good job of optimizing it, right? So there's whole literature on single assignment forms value tracking, constant propagation. Compiler's really good at that stuff. Sorry.
But if you don't cache it, then it assumes that it must be able to change.
Yeah, if it's these 2 pointer loads, it says, oh, I don't know who's going to change this. So it has to leave it alone.
I believe compiler is still able and allowed to optimize that.
So
Because if you don't want compiler to optimize that, then you say atomic. If you don't say atomic, then compiler is free to assume that nobody else is modifying those members, so it can.
So
atomic. In this case, atomic.
So now you're getting into whether or not any optimizations introduce data races. And there are certain situations in which optimizations can avoid data races. But the main thing here is that in my advice to you, I don't know whether you're calling a subroutine, what that subroutine might modify. So the compiler can get rid of redundant loads in a lot of cases, but it can't get rid of them in all cases.
I'm talking about this particular case when you have a member function, and in that member function you're reading some field twice without modifying it in between. Then in this case, compiler can being guided by as-if rule.
So if you have if the member function you're writing itself calls another member function, and the compiler cannot see the body of that,
Yep.
then it has to assume that that member function might have modified it, so it has to reload it, right? If you, as the programmer, do read caching, now it's a different object, and calling the member function cannot change what you've cached. Okay? Often that's what you want. Sometimes you actually do want to see the modification, in which case you don't do the read caching. But my general rule is I want to, by default, be able to read cache all of the data members when I'm writing a method. If I can't do that, I want to know that, right? It's the cases that I can't read cache that are the important ones, right? Those are the ones I really want to mark as being not read cacheable. Sir.
For inlining, do you have any horror stories in practice where you've seen inlining physically increase code bloat and harm perf as a result? We observed when we turn on inlining in our CRT, the CRT shrunk by 4 kilobytes, which was nice and unexpected. But I don't know if there are actual horror stories you've seen.
So I think your colleague has a horror story.
Windows got really annoyed when we don't do inlining, so they forced us to add force in inline, or as we call it, inline. Damn it! I'm the developer, I'm the coder, I know better. You inline this function. They're banning it because of code bloat, because they inline everything. So, in my opinion, inline and force inline. Don't add them to your code. Run the optimizer profile again when you know exactly where it's going slow. Judiciously add a few inline directives.
So I've seen a case where, due to inlining, a chunk of code got bigger than one page. And now you start getting in highly contended places, you start getting cache bouncing around, you start getting potentially TLB misses. So most of the time, the code bloat doesn't matter all that much. But here's the kicker. Most of the time, the difference in performance between an inline function and a non-inline function is not measurable. Because that difference is really only measurable in your hot code. So now, that's if it's big, right? If it's small, then inlining is actually a benefit because now you're reducing the code size because the inline function can be smaller than the call. and you're avoiding it bouncing around in the instruction cache and so forth. So if it's small, inlining is a good thing. When it starts to get large, inlining often costs more than it gets you. But the performance analysis tools are your friends.
I think it was from this year's C++ and Beyond. Alex Andrescu had a talk where they did performance analysis at Facebook, large scale in their code. And he said it was worth the price of admission. He gave a few little tweaks where they increased the threshold using GCC of where it did automatic inlining, and it saved them like 10% performance improvement. I don't know about the code size, but just in terms of sheer performance latency.
Yeah. There's no substitute for experiments here.
Profile and do it again. Make sure you understand exactly what the codes do.
Yes. So we've all heard that portability is good. However, with IBM System 360, we have machines that can do business, technical, large and small. All other architectures are going to fade away. You will never have to port your code again. The IBM 360 will save you.
Well, I think that's sort of true. There's a lot of IBM 360 code out there that's never been ported.
So the best thing you can do for portability is follow along. Conform to the formal requirements in the standard for programs. Aim for compilers that are a bit behind the standard. You don't want to be quite on the bleeding edge if you want to be portable. Authors write and publish and talk so that you don't have to suffer so much. Go ahead and pay attention to them. Recently we've gotten a huge raft of excellent tools in. Those things will find all kinds of bugs, performance issues. Go ahead and make use of those. They'll save you both time and money. You want to choose portable types. Use STD types for representing user data, the STD int types for representing user data. They have a fixed size. You know exactly what you're getting on any machine. Use size T types for indices and sizes. That means you can use up all of whatever machine you're on. Use the legacy types for interacting with existing APIs. Git char is always going to return an int. Let's see if we can sum up. First thing is, value types are an investment. It takes time to develop a good one. There's a lot of issues to look at. But once you're done, you have opportunity for lots of profit. The clients of your type don't have to worry. Their development times are faster. There's a handle out there for when things go wrong. They can breakpoint on member functions of these value types. All kinds of goodness in debugging and performance analysis. And you potentially get reduced execution time because you've done a lot of careful optimization in the implementation of the type. Now the compiler can pick up all of that work, just slide it in, and carry on. And since you've spent all this time on this new type, consider sharing it with the rest of the world. There are plenty of venues in which to do that.
So one of the things you talked about is the fact that restrict doesn't work yet in C++, and it's bastardized from C99. But all compilers have it. And everybody loves it when they can make it work and use it. What we're trying to do now is there is a proposal working through a standing committee where we're trying to create a better form of restrict like semantic without using the word restrict. The problem with doing it in C++ is you have to deal with a lot more troublesome things, like what happens when you have overlaid memory that's partially overlaid on top of each other. There's a lot of deficiency with the C99 variants. For instance, it doesn't survive when you get passed in through parameters and things like that. It was an insufficient specification.
Can you give us an introduction on what restrict is?
Okay, so restrict actually is a quick idea of an optimization that was sort of following what Fortran had. And it says that these things that I'm passing in do not alias each other. I promise, I swear to God, they don't. Okay? If they, by some chance, you pass in the same thing when you actually call them, And then in that case, caveat emptor. Yeah, exactly. All that goes off. For most of the time, it is true. It's for some pathological cases, it isn't. It's bad. Okay. So it is a proven optimization technique, and it does work. Everybody swear. You know, the problem is this, there's no rules for C++. All those rules were created for C, and so we're trying. And I'm one of those trying to push this proposal through. It's got a tremendous welcome through the community. They feel that it's really needed. So we're hoping to solve one of the problems that way. So thanks.
Excellent. So, any more questions? Yes.
Just a note on your point about size t.
Yes.
I don't terribly disagree one way or the other on signed, unsigned. That's a whole complicated issue. But I think the argument for use size t so you can address everything is a bogus argument. Like, I have never seen a 32-bit system that had a vector of 4 billion things allocated at once. Like, I don't think you can use that last bit in practice. So this argument is kind of...
So you can use the signed size t, s size t.
Right.
You can go ahead and use that. The problem is that many of the standard classes use size t anyway.
Right.
So you're now inducing a type conversion.
Yeah. That argument I totally buy. Like,
So-
use size t because the spec compatibility, totally with you.
So I did not personally have this bug, but it did show up in my group where an application did start to fail because it wanted to allocate a object that crossed the middle of the boundary.
As in,
So
its buffer crossed that boundary, or the size of it did?
it was more than 2 gigabytes, and it straddled the line
On a 32-bit
on a
build?
32-bit architecture. So
Really?
So the net result of that was, you know, we also sell 64-bit machines. Why don't you use one of those?
Yeah, I mean, that seems like a good answer, but like, how did you have, you know, bits for addressing anything else in there? I mean, it doesn't.
Yeah. Okay. Any other questions?
Yes, you mentioned regarding literal types, one of the advantages they can be used as non-type template parameters.
Yes.
If I understood correctly. Are you sure about that? 'Cause I
believe
had
so,
a
yeah.
reasonably good. Okay.
Yeah. So let me warn you, though, when you start doing that, your mangled names could get kind of big. But it's, you know,
Okay.
you know, we have gigabytes these days for a reason.
I'm curious if you can suggest an example, like in either in a standard library implementation or an open source library that's commonly available, of a class, a value type class that is well implemented and follows all these guidelines that we could maybe go home and look at and follow the example for our own types.
Oh, that puts me on the spot. I don't have one that does all of this. There have been some implementations of a string that's not a container. Those might follow most of them. UUID? So yeah, boost UUID. Some of there might be some in the standard library. I'd have to look. But you make a good point that a tutorial with more comprehensive examples than I have in this talk would be good. Any other questions? Thank you. I'll be hanging out.